Hello and welcome to the second and final video for the Thanksgiving week linear algebra. In this video we will talk about some more series and utilize two tests to see whether they converge, as well as we will talk about the idea of alternating series, which are a specific type of series that are often easier to prove convergence for. We'll start out with this series here. We got the sum from n equals 1 to infinity of 5 to the nth power over n factorial. I want you to quickly think and look over the divergence test, the limit comparison test, and the series comparison test, and see if you can identify a way to do this series. So again, I would advise you to pause the video for maybe a minute, look over the past test, and see if there are any issues with them. What you should notice is we haven't done any series that we can compare this with. So the series comparison and limit comparison don't work. We take the limit as n approaches infinity, we get 5 to the infinity over infinity factorial. Moreover, infinity factorial, which by the way, as a reminder, n factorial means we multiply 1 times 2 times 3 times every positive integer in order up to n. So infinity factorial causes difficulties with limits. In case you're wondering, no, there is not a simple derivative of n factorial. So L'Hopital's rule on this limit for the divergence test doesn't work. And as it turns out, this limit does actually go to 0. However, showing the limit of the nth term going to 0 for a series is insufficient to show convergence. For that reason, we need a different type of test. The test we introduce is called the ratio test. For the ratio test, we compare two consecutive terms. We compare the term n plus 1 with the term with n. We then take the limit of the absolute value of these terms and we look at what happens to the limit. If the limit is between 0 and 1, the series converges. By the way, it is worth noting that an absolute value has to be greater than or equal to 0, so the 0 on the left is a mere formality. The key thing behind the limit being less than or equal to being less than 1 means the terms are decreasing once you get towards the end. And if something decreases, if a positive number decreases forever, think about it. There's only so much you can go and still be positive. So if we're told that we have a positive sequence of numbers and they're decreasing forever, eventually they have to get infinitely close to 0. And so this is the idea behind the limit comparison test, is the next term is getting smaller forever for convergence. Now, if the next term is getting larger, meaning the ratio is greater than 1, the series is going to diverge. And of course, the extreme case of that is if the next term is getting infinitely much larger, which would be a limit as n approaches infinity that's equal to infinity. Personally, I'm going to group these two for the divergence as being one and the same. Because really, to me, infinity is greater than 1. I realize the fancy mathematicians out there will point out that infinity is not a real number. However, whatever way you cut it, infinity should be greater than 1 in terms of perception. And then the annoying scenario that we're not going to get to very much, and that is a ratio test can be inconclusive. So if the limit as n approaches infinity of your ratio is 1, That means you can't use this to determine convergence and you have to do something else. So that would be the case of frustration. So now, let's move on and let's use the ratio test to determine convergence of some series. So let's apply the ratio test to the series n equals 1 to infinity of 5 to the nth power over n factorial. This test has a reasonably simple setup in that we're going to write what we have on the inside with n plus 1, and then we're going to write what we have on the inside just as it is with n, and we're going to take the limit as n approaches infinity. So this is our set. We don't need the absolute value once we plug in the terms, because the smallest this will get is still a positive number. Any factorial will be positive, and 5 raised to any power will be positive. The next step in this limit is to divide the fractions and rewrite it. So at this point, we note that we're dividing exponentials on the right side of this. For dividing exponentials, meaning 5 to the n plus 1 and 5 to the n, we subtract the powers. Subtracting n from n plus 1 gives 1, and 5 to the first power is just 5. The next thing to do is to write out n factorial and n plus 1 factorial in terms of key terms, and we're going to look to cancel. So n factorial is 1 times 2 times going on up to multiplying by n. n plus 1 factorial is 1 times 2 times going up times n plus 1. At this point, my apologies for the error right there. I should have written limit as n approaches infinity. Now that error is corrected, at this point we note that both the top and bottom of a fraction are multiplication, and that means that we can cancel out any like terms. So that means we can cancel out 1, 2, and all the way up to n. Everything there cancels out. The only terms that are not included in both the numerator and the denominator are 5 and n plus 1. This leaves us with 5 over n plus 1, and at this point we can plug in infinity, giving 5 over infinity, which is equal to 0. Since 0 is less than 1, this series converges. A similar process can be applied for n factorial over e to the n, that is the series from 1 to infinity. I will show the process, I will give a quick explanation, and we will then move on to the next topic. So the process is the same for this second series. Again, we take the limit as n approaches infinity. We have the ratio an plus 1 over an. We write that out. We divide the fractions. We then use the rules of exponents to note that en over e to the n plus 1 is just e. We then write out the factorials and cancel almost everything. We then end up with n plus 1 over e. So that means that we have infinity over e, and infinity divided by any real number, and by the way, e is just 2.718 going on. Infinity divided by any real number is infinity. So that's our result. Infinity is greater than 1. So the series diverges. One note is that we do need to say that the limit is greater than 1. Because remember, 1 is inconclusive, so I apologize for that error that is now corrected here. So now let's consider another type of series that does present issues. So we have the series from 1 to infinity of 5 to the n minus 1 raised to the n over n squared plus 3n raised to the 2n. Now, I ask you the question, do you really want to take a limit of a ratio involving this series? Personally, plugging in n plus 1 to both the top and the bottom and taking a limit is a nightmare. And by the way, it most likely is doable in this case because you could raise both the numerator and denominator to e to the ln. However, fortunately enough for us, there's an easier way. Because you notice, okay thing, how can you get rid of a power? Well, the answer is take a root. As it turns out, there is a series test involving the nth root, specifically known as, in part, showing the laziness of mathematicians when it comes to labeling or naming, the root test. So, the root test says we can take the limit of the nth root of a term, and if that limit, and by the way, it's the absolute value because an nth root, if you take an even number root of a negative number, it doesn't exist, so we have to take an absolute value to make sure that our answers actually exist. Usually that's a moot point. But anyway, if we take the limit as n approaches infinity of the nth root of the nth term, and that limit is less than 1, the series converges. If the limit is greater than 1, the series diverges. So in terms of what numbers the limit equals, it's the same as the ratio test. Just now, instead of taking the ratio of terms, we're taking the nth root of terms. And again, to be clear, the inside of the root is just the nth term. We are not tacking on anything to the nth term when we put it inside the root. And yes, similar to the ratio test, if we happen to get the limit being equal to 1, the test is inconclusive. To save all of us the frustration, I will not be giving you any problems where this is the case. So, let's apply the roots test to determine whether two series converge. So, let's take a look at, first of all, the series from 1 to infinity of 3n squared minus 2n plus 4 over 5n squared plus 7n minus 1, everything raised to the n. To apply the root test, we are going to take everything that's inside the sum, and we're going to take the nth root of it and take the infinite limit. So, all we do for this test to start it up is we take everything that's inside the series and we put on under an nth root. Now, this has a clear advantage here, and almost always when we use this test, we make sure we have the advantage. And that is we're taking an nth root of an nth power. So, conveniently enough, the root and the power cancel off. From here, we use the technique of dividing by the highest power of the variable on the denominator and using that to calculate the limit. This limit can also be done using the L'Hopital's rule, although because the second power on the top and on the bottom, L'Hopital's rule would have to be done twice. So, because we have done both those methods on previous problems, I'm going to just give the answer to this limit, and the answer to this limit is 3/5. Since 3/5 is less than 1, this series converges. To save time, I am going to skip the solution to the next series on the video. It will be shown on the notes. And I'm going to move on to one more where we apply this test. So, I want to give an example of a series that diverges from this test. And so this is a series that is foundational level that diverges. And again, given the timeline of this course, I am not going to require problems beyond foundational level. If you wish to do some of those, I would be happy to provide explanations. However, on homework assignments and on tests, the problems I will be asking you for series convergence will be foundational level. So let's consider this problem. And the start of this problem is very similar to the other problem. So again, for this problem, we take the nth root of the nth term, The root and the exponent cancel out, leaving us with an infinite limit that we have encountered similar to 1's 2 before. You can either then use L'Hopital's rule or divide by the highest power of the variable. And in this case, we end up with 7 over 2. Now think about it. What is a key difference between this answer and the previous answer? So the key difference here is this is greater than 1. And so if the limit of the nth root is greater than 1, that means the series diverges. So that's the extent that we're going to go over the root test, is taking limit as n approaches infinity of the nth root of terms for a series that fit, which almost always involve the numerator and denominator raised to an exponent, some of the time different exponents, an example of which will be shown on the posted notes, and then seeing if that is greater than 1 or less than 1. Again, if the limit of the nth root is equal to 1, we would have to do another test. However, when it comes to series convergence, that would be beyond the level we have time for in this course. So now let's move on to a different type of series called alternating series. So an alternating series is a series whose terms go between positive and negative. So that means that every other term is negative, and again, we just constantly switch between positive and negative. Moreover, every alternating series can be written as -1 raised to a power that's either the nth power or the n plus 1 power. These series come up a fair amount. It will be seen later in the course, by the way, not during the break, so you don't have to worry about this, that sine and cosine can each be written as alternating series. And so these series are of particular importance. Another nice thing about these series is determining convergence of these series is less difficult than it is for series that are not alternating. So alternating series tend to converge more often than series that are not alternating. And an example of this is, as much as the sum from n equals 1 to infinity of 1 over n diverges, if we make the top be -1 to the n, which is an alternating series, -1 to the n over n from 1 to infinity, that converges. Similarly, the series, which is similar to a p-series of 1 over the cube root of n plus 5 going from 1 to infinity, that diverges. Yet -1 on the top of that converges. And so with alternating series, more alternating series converge as opposed to non-alternating series. There are some additional terms to this, so if you are interested in this, I would encourage you to look up conditional convergence versus absolute convergence. However, we will just be talking about convergence, conditional convergence, and we're just going to call it convergence. So we will only be talking about conditional convergence, and we will be referring to that as convergence of alternating series, since the series as written, if it's an alternating series, conditional convergence tells you the convergence without doing anything else to what's written. So, to prove an alternating series converges, and again, I remind you the two main forms of alternating series are either -1 raised to the n times some term, or -1 raised to the n plus 1 times some term. We can prove the series converges if we can either show that each term is positive and the next term is less than the term before it. If we can show that every term is positive and that is every term aside from the -1, if we can show that every b sub n is positive and decreases for the next term, then it converges. The other way is to show that the limit as n approaches infinity of Bn is 0. Now, I remind you, these tests only work for alternating series. So these tests of convergence do not work unless the series is alternating. With that in mind, let's apply these tests to some series. The first series we will apply these tests to is the sum from n equals 1 to infinity of negative 1 to the n plus 1 times n over 2n. First of all, when you're looking at these, it's not a bad idea to make your own guess whether it converges initially, because that can help you determine whether you should be looking for the limit going to 0, or whether you should be looking to see if there's a contradiction to one of the two statements, that either the limit does not go to 0 or that there is a term down the line that is greater than the previous term. Now, if you think about it, n over 2 to the n, that in terms of graphs, an exponential should be much larger than a single variable. So a good place to start with this first one is to take the infinite limit of n over 2 to the n. If we plug into this limit, we will get infinity over infinity, which is indeterminate. So in this case, it's best to use L'Hopital's rule. If you think about it, and I encourage you to do so, the derivative of n is 1. So using L'Hopital's rule immediately makes the top part of the limit very simple. And then the derivative of 2 to the n is 2 to the n times ln of 2. If we plug in infinity to this resulting limit, we get 1 over infinity, since any number greater than 1 raised to the infinity power is infinity, so this becomes 1 divided by infinity, which is 0. This fits the second option of the alternating series test, and so this series is convergent. Prior to doing the two series we have here involving sine, I want to do one that is perhaps a bit more intuitive. So let's take a look at this series in the bottom right corner, the sum from n equals 1 to infinity of negative 1 to the n times 2n plus 1 over 3n. Again, intuitively think to yourself, should this series converge? So, again, a good starting place is to take the limit as n approaches infinity of the inside. Taking this limit, we can use L'Hopital's rule, which would give the limit as n approaches infinity of 2 over 3. In this case, there's no variable to plug in, and so the resulting limit is just 2 over 3. Since this limit is not 0, immediately the series is divergent, as it then fails that part of the alternating series test. In this case, the next two series I'm going to go over go above the level of which I'm going to require on a quiz. If I choose to put problems similar to either one of these on a quiz, they would be extra credit problems. So for those of you that have other obligations or are already mentally exhausted, which is perfectly understandable, you do not need to watch the remainder of this video. For those of you that want to see more complicated examples of convergence, I will include these two series as part of the video, since this is kind of an add-on. So let's start out here with the sum from n equals 1 to infinity of negative 1 to the n plus 1 sine squared 1 over n. Now, in this case, our limit ends up being nice. So this first one sine has a very convenient property. If we plug in infinity for n, 1 divided by infinity is 0. Moreover, sine of 0 is 0, and 0 squared is 0. So, in this case, the limit as n approaches infinity is 0, and this series converges. Now, let's look at this last series. In this last series is where you cannot use a limit. The reason being is if you use a limit, if we were to take the limit as n approaches infinity of sine squared pi over 4n, it does not end up existing. The reason it doesn't exist is this oscillates up, and is sine of infinity oscillates up and down forever. Moreover, this is just the limit of sine. We do not have any other functions that will either expand or squeeze this. Again, the squeeze theorem, if this was over something that went to infinity, then we could say it was 0. Or, on the other hand, if it was multiplied by something or something was subtracted, then we could also make a ruling of where it's going to go, because sine is constricted between negative 1 and 1. However, when it's just sine, at infinity, sine is a blur between negative 1 and 1, so we cannot say it is equal to any number. That means we have to look at one term versus the next. Now, the fact it is pi over 4 times n, and n is an integer, results in patterns that we can utilize. If we write this out sequentially, using just the first 8 terms, we get sine squared of 1 pi over 4, sine squared 2 pi over 4, 3 pi over 4, and on up. Now, once we get to 8 pi over 4, think to yourself, what is 8 pi over 4 equal to, and what will happen with the next number in this sequence? 8 pi over 4 is 2 pi. That means this pattern of 8 terms will repeat. So let's consider what this pattern of terms is using the fundamental trig values from the unit circle. Using the unit circle and noting that the square root of 2 over 2 squared becomes 2/4, which is 1/2. We get these 8 to be 1 over 2, 1, 1 over 2, 0, 1 over 2, 1, 1 over 2, 0. And then it will repeat. Meaning, if we write out the terms of this series, which alternate between positive and minus, we will get the following. Notice that in a number of places, the next term is greater than the previous term. So in this case, an plus 1 is not less than or equal to an. Or correction, using the terminology of this, bn plus 1. So this means that by that part of the alternating series test, this series is divergent. That concludes this video. Again, I thank you for watching this video. I hope you have a great week away from campus. A happy Thanksgiving if this is before Thanksgiving. And I will see you next week. Bye.